Hey guys, so this is section 9.3 where we talk about applying the ideal solution model to binary systems. So binary systems means there's two components. Both of those components will obey Raoult's law for an ideal solution, which means that for component 1, the pressure above the solution is equal to the mole fraction of that component in the solution times the vapor pressure of the pure component. And same thing for component 2. And remember that the mole fractions have to add up to 1. Total pressure is just the sum of the partial pressures. That's Dalton's law of partial pressures. Substituting in here for each of the partial pressures, this for this, and same thing for component 2, and also using the fact that mole fraction 2 is equal to 1 minus the mole fraction of 1. We get this equation. If we rearrange this a little bit, check the algebra yourself, we get that the total pressure is equal to the vapor pressure of the second component, pure second component, plus the mole fraction of the first in solution times the difference in the vapor pressures of the pure components, 1 minus 2. Remember that, we're going to use that in a little bit. And this just shows a graph of the pressure of each of the components versus the mole fraction of one of the components. In this case, it's a solution of benzene and 1,2-dichloroethane. I'm not sure why they didn't use benzene and toluene. They do it for everything else, but it's still pretty close to an ideal solution. There is some deviation. Pretty much every solution is going to have deviation. The solid lines are extrapolations of experimental data, and the dashed lines are from Raoult's law. Pretty close, but not exact. And this line up here is the total pressure. All right, so far when we talk about mole fractions, it's always been mole fraction in the liquid phase in the solution. We're going to talk about now how to calculate the mole fractions in the gas phase. We're going to call the mole fraction in the gas phase, say, of component 1, Y1, as opposed to like Chi1 for the solution. So this is the in solution, this is in the vapor phase, the gas. And we do know that the mole fraction in the gas phase is just the partial pressure of that component divided by the total pressure in the gas phase. And we know that the partial pressure is equal to the mole fraction in solution times the vapor pressure of the pure substance. That's Raoult's law. And we just showed a minute ago that the total pressure is equal to this. Remember I said we're going to use it in a minute? Here we are. Rearranging this, doing some algebra, solving for the mole fraction of the first component in the liquid phase, Chi1. Check my algebra here. We get this right here. I'm going to use that. So remember that one. Now we're going to, what we're going to do is the expression we just derived for the mole fraction of component 1 in the liquid phase, Chi1, we're going to substitute it here in the expression we got for the total pressure on the first slide. And when we do, we get this expression right here. And do some algebra, again check the algebra. We get that the total pressure is equal to this expression right here. Or if we needed to, we could solve for the mole fraction of that component 1 in the gas phase. We would get this expression right here. So notice this is an inverse relationship between the mole fraction of component 1 in the gas phase and the total pressure. Up here, there's a direct, a linear relationship between the mole fraction of component 1 in the liquid phase and the total pressure. So that they're different. There's a different relationship. I'm going to see that. So this graph shows the pressure versus the mole fraction, and this, benzene is what the component that they picked here. This is the mole fraction of benzene in the liquid phase, and this is a straight line. Okay, it's down here beneath this line. It doesn't make any sense. There's no solutions that make sense, so we just ignore it. But this is basically the equation of a straight line, y equals mx plus b, right? So if we plot the total pressure versus the mole fraction of one component in the liquid phase, we get a straight line with the slope here, y-intercept there, and that's what this shows right here. Remember that we have an inverse relationship between the total pressure and the mole fraction of that same component in the gas phase, y1. And that's what it looks like here. Plot the total pressure versus the mole fraction, in this case of benzene in the gas phase, and it looks like this. Now, to look at the gas phase and liquid compositions under the total pressure, we graph both as a function of the average composition of a component, benzene. So we're going to use benzene. We could use either one. So we're going to call the average composition of benzene Z benzene. And it's just the total moles of benzene, which is the moles of benzene in the liquid phase. That's what this term means. Plus the total moles of benzene in the vapor phase. That's this term. Divided by the total moles everywhere, which is the moles of toluene in the liquid phase, moles of toluene in the vapor phase, moles of benzene in the liquid phase, moles of benzene in the vapor phase. So now we're looking at the benzene-toluene system, and which is just equal to the total moles of benzene over the total moles. That's Z benzene. So if we do that graph, we get something that looks like this. This is called a PZ diagram. And it really is a combination of what we just saw. The total pressure versus the mole fraction in the liquid phase, total pressure versus the mole fraction in the gas phase. See that right down here, this part looks like that. This part looks just like that. So in this diagram right here, any time you're in this area right here in the liquid region, the Z benzene, the average composition of benzene or whatever component you're talking about, it's just the mole fraction in the liquid phase because it's all liquid up here. Oops. Likewise down here, it's just the mole fraction in the gas phase, Z whatever, benzene or whatever we're talking about, is equal to the mole fraction in the gas phase because everything is a vapor down here. In here, between these two, in this region in the middle, this is the coexistence region, right in here. So in that liquid vapor coexistence region, we have two components, benzene and toluene, and there's three independent state variables: pressure, temperature, and Z benzene. We could use Z toluene here, but they're not independent. There's this equation that connects them. We know the Z benzene plus Z toluene has to add it to 1, so they're not independent. And I don't know if you remember, but we developed the phase rule. We presented the phase rule in section 8.3, and this is a modification of it for a system that contains C components, number of components C. The phase rule becomes the number of degrees of freedom F is equal to the number of components minus the number of phases plus 2. So for example, in the 2-component benzene toluene solution, C is 2, so we get the number of degrees of freedom is equal to 4 minus the number of phases. So in a single phase region, like liquid or vapor, we have 3 degrees of freedom. And in the coexistence region, where there are 2 phases, liquid and gas, we have 2 degrees of freedom. Now in this graph right here, temperature is fixed. So that takes away 1 degree of freedom. So in this area of the graph, there's only one phase, but 2 components, but there's only 2 degrees of freedom. Same thing down here. And in the coexistence region, there's 2 phases, so there's only 1 degree of freedom. So in here, if you looked at a fixed value of P, the pressure, then that you follow that line across wherever that line intersects the this line right here, the coexistence region. The value here for Z will be the mole fraction in the liquid phase. Wherever it intersects this line here, the other side of the coexistence region, that value of Z will be the mole fraction of that component in the gas phase. So, there we go. So here's an example. Let's say we have that many moles of benzene, that many moles of toluene, put them in a cylinder, frictionless, massless piston, so our usual situation. And we're going to assume they form an ideal solution, so they obey Raoult's law. And we're told that at 298 Kelvin, the vapor pressure of pure benzene is 96.4 torr, pure toluene is 28.9 torr. We're going to start out this system where the pressure above the solution is 760 torr, and gradually reduce the pressure. So we're way above the vapor pressure of either component, so it's going to be all liquid at that point. As we start reducing the pressure, we're going down in that PZ diagram, we want to know what pressure do we first start to see vapor appear, and what are the mole fractions of benzene and toluene in the vapor phase at that pressure. So all we do is we calculate the mole fraction in the liquid phase, which is what we're starting with, moles of benzene. This number down here, it's just the sum of the two moles, 3.14 plus 7.239. And we get the mole fraction for benzene in the liquid phase, mole fraction for toluene in the liquid phase being this. We could have done 1 minus this, got the same thing. Total pressure at that point is going to be the partial pressure of benzene, which is the mole fraction in the liquid phase, times the vapor pressure of pure benzene, which is given right here. And likewise for toluene, plugging in, we get the total pressure being 49.3 torr. That, you guys, is the pressure at when we get down to that pressure when we would first start to see vapor forming. To find the composition, we just need to find the mole fraction of the two components in the vapor phase at that pressure. So we get the mole fraction of benzene in the vapor phase, Y-ben, is equal to the partial pressure over the total pressure. Partial pressure, just like we did up here, is just the mole fraction times the vapor pressure of the pure substance. Total pressure we just calculated. So we get the mole fraction of benzene in the vapor phase at that pressure, being 0.591. Vapor pressure of toluene in the vapor phase would be 1 minus that. And there we go. Now the lever rule. So if we look at this same diagram, the PC diagram, and we're blowing up a region of it right here. By the way, these lines that are constant pressure, they go across the liquid vapor coexistence region, are called tie lines, TIE. And we're going to use this. So the distance on this tie line from L to B is just the Z here minus the Z here. So if we look down here at this one here, this is just Z of benzene minus, at this point right here, we're right on the line, so this is just the mole fraction of benzene in the liquid phase minus chi benzene. And so another way of writing Z benzene is total moles of benzene divided by the total moles, and mole fraction of benzene in the liquid phase, just moles of benzene in the liquid phase divided by the total moles of benzene in the liquid phase. So this is vapor and liquid, this is just liquid for benzene. Likewise for the BV, or nu, whatever, length, this length from here to here, it's just this value down here on the x-axis minus this value. So this minus this, which is just the mole fraction seen in the gas phase minus the mole fraction Z benzene, and mole fraction of benzene in the gas phase, Y-ben, is just the moles of benzene in the vapor phase over the total moles in the vapor phase, and Z benzene is the same thing we just saw before. So we're going to use these, do a little bit of algebra to get our lever rule. So what I did here is I took that first equation, multiplied both sides by the total moles in the liquid phase, and so it canceled out over here. Remember, we had it on the bottom here, and we have it up here, and it's in front of LB. This LB represents the distance from L to B on that tie line. Likewise, for the second equation, I multiplied that one through both sides by the total moles in the vapor phase. Cancel it out here. We have it up here, and it's multiplied by here. And again, BV, B nu, whatever, is the distance on that tie line from B to nu. Subtracting these two equations, get this minus this is equal to, now there's just some algebra in here, so I pulled out total moles of benzene over total moles from here. We get this expression right here. And simplifying it further, we get total moles of benzene over total moles times total moles of liquid plus total moles of vapor minus moles of benzene in the liquid phase plus moles of benzene in the vapor phase. But this in the parentheses here is just the total moles, and this right here is just the total moles of benzene. So we just get total moles in the liquid phase times LB minus total moles in the vapor phase times B nu is equal to total moles of benzene. Because the end total here and here cancels, we get total moles of benzene there. And this is total moles of benzene, so that's 0, which gives us the lever rule. So that's what we got. So that means that we can say that the total moles in the liquid phase times LB is equal to total moles in the vapor phase times B nu, or the ratio of the total moles in the liquid phase over the total moles in the vapor phase is equal to B nu over LB. But LB we saw is Z ben minus chi ben, and B nu is Y ben minus Z ben. Plugging those in, there we go. That's the lever rule. What good is that? What that does is that lets us calculate, let's say we know everything but this. We can solve this for the moles, say, of benzene or of any component in the gas phase. Or, can solve for anything in here we don't know really. Usually it's going to be the moles in the gas, or the mole fraction, in the gas phase.